Next up, we have Shreya Anand, who's going to be telling us about the first LST Rubin follow-up of a gravitational wave event and TOO trigger.
All right, thank you. Hey, hello, everyone. I'm pleased to be back here at Caltech. Today, I'll be talking to you about the first Rubin target of opportunity search for a subsolar mass merger candidate, which may or may not be a neutron star merger. And I'm presenting on behalf of the entire Rubin ToO team, which is all of these names here and more. So let me start off by giving you a brief introduction to the Rubin ToO system. So initially, SIMA would receive an external alert from, for example, LVK or IceCube or another external experiment. And once that is ingested by SIMA, you would get the alert is parsed for alert quality criteria, which have been defined in the Rubin ToO white paper and also described here in this technical paper. Once the alert passes quality criteria, it is sent to the Rubin engineering facilities database and then ingested by the Rubin scheduler. The scheduler creates an observing strategy depending on the sky map and properties of the event. Rubin executes the observations and then it's passed on for prompt processing and alert production. In some cases, in some rare cases, if this is a non-standard ToO, the Rubin ToO Advisory Committee may decide to go after it, even if it doesn't pass the nominal alert criteria. So just to give a bit of context, I'm particularly very excited about Rubin's capability of finding EM counterparts to gravitational waves. As Jillian very nicely motivated in her talk, Rubin, due to its depths reaching down to 25th magnitude in G band and R band, has a great potential to track kilonovae to later times than other optical facilities. Here you can see a kilonova light curve that is at 350 megaparsecs and the proposed gold event strategy, where a gold event corresponds to a neutron star merger localized to better than 100 square degrees. So here you can see the proposed strategy in the Rubin ToO white paper is to get epochs, several epochs in multicolors on the very first night and then in 2 filters on subsequent nights. It changes a little bit, of course, based on the size of the localization. But with this strategy, you're able to track the light curve to several days after the merger time. So as Jillian also mentioned earlier, we are now in the gap between O4 and IR1. IR1 will provide a great opportunity with overlap with Rubin and the LIGO facilities to detect the next kilonova. But I do want to talk about an exceptional event that happened at the very end of O4, which we triggered on. So S251112CM was detected on November 12th of last year. It was quite exceptional because of its properties. So in particular, it has SSM, which is a property describing the probability of one of the components being a subsolar mass merger of greater than 99%, and a chirp mass of between 0.1 and 0.87 solar masses, which indicates that if the 2 components are roughly equal, then both of them would have had to be subsolar mass. It passed the false alarm rate criteria and was localized to 1681 square degrees on the sky at a distance of 93 megaparsecs, so relatively our backyard. Many teams followed up this event because it was quite exceptional. So here you can see the sky map of the event, which is spanning both the northern and southern hemispheres. So you might ask, what is a subsolar mass merger? And the answer is, I don't think many of us really know. Of course, there have been many theories proposed. One is that it could be a kilonova from a binary neutron star merger, but something that is quite non-standard or very strange looking kilonova. Or it could be perhaps a superkilonova, in which you have a massive star that collapses to form a black hole. And in the accretion disk fragmentation occurs, resulting in the formation of new subsolar mass neutron stars in the disk, which then merge to form a kilonova. So you get a supernova and a kilonova that are both observable. And finally, it could be primordial black holes that survived from before the first stars formed. And in this last case, we probably wouldn't expect an electromagnetic counterpart. So due to the exceptional nature of this event, Rubin leadership and the ToO advisory board decided to go ahead and trigger, even though Rubin was actually in this unique phase between commissioning and operations, in the early operations phase. We covered a probability of 40%, which corresponds here to the southern lobe of the gravitational wave sky map. So here you can see the coverage map, and the color bar shows the number of visits by Rubin over the course of the campaign. We took 30-second images in G and I bands, and the observations spanned 4 epochs from nights 0 to 6 after the merger. So this was, well, the observations started 2 days after the merger. So nights 0, 2, 4, and 6 after that. And in just 30-second exposures, Rubin was able to reach a depth of 24.4 mag in G and 23.6 in I, which was amazing. So the main challenge that we faced was that there were no existing templates, so no way of automatically generating alerts. We had to develop a custom image processing task, so this is particularly done by Bob Armstrong and Erin Howard, who created DCAM templates from the DES, DELV, and DK datasets, and then ran the LSST's standard data release production pipelines to get photometry on all of the detected alerts. So we started out with 8.7 million DIA objects from the initial processing. And then we proceeded to apply quality cuts, including eliminating dipole artifacts, negative sources, and sources that had low reliability scores. We required 3 detections and 2 filters and multi-night detection. And then, of course, required that the candidates fall within the 95% probability contour. So that leaves us with 160,000 DIA objects, where 1 DIA object corresponds to 1 candidate. And from there, we applied light curve-based filtering. So we eliminated anything that had flat evolution, requiring candidates to be either fading at some rate or rising. So for the initial processing, we covered candidates that showed any kind of fading behavior, and also fast rising candidates. Shown here, we also differentiated the candidates that appear to be a little more fast fading, so greater than 0.3 mags per day, which is motivated by the typical fade rate of kilonovae from models, and also candidates that were within 50 kiloparsecs of a NED galaxy in the volume, using the NED GWF service. Finally, we went through and tried to filter out all of the possible kilonova imposters. So we eliminated AGN-like candidates that were nuclear through a WISE and Milli crossmatch. We got rid of stellar sources through Gaia crossmatches. We removed galaxy-like candidates. And then finally, we ended up with 1,300 objects that we had to visually inspect. And following the visual inspection, we ended up with 70 candidates that we then cross-matched to legacy survey, and we found that about 30 of them were too distant, so greater than Z of 0.3 to be consistent with the localization. So we ended up finding some real transients, and here are some Rubin cutouts from the campaign. This is a G-band image. You can see the host galaxy here. Here's the transient AT2025 Aiden, which is 30 arcseconds away from the NEG galaxy in the gravitational wave volume. and the difference image shown here. And these are templates taken from the constructed DCAM templates from the image processing task. So yeah, the process works. We're able to find real transients. It was super exciting. And here is the light curve from Rubin showing this candidate fading in different bands. Okay, so to summarize, we had 70 candidates in our final shortlist. As I mentioned, 30 of them were too high of photo Z to be consistent with the localization. And 15 of them were detected by other surveys, which means that we had many new candidates that were released, but none of them were consistent with kiloneway. So this exercise showed that actually systematic filtering, even of a large volume of candidates, yields a digestible number of candidates that can be released to the community. And based on our non-detection of a kilonova, we can actually start to place some meaningful constraints on the kilonova model. So this is a compilation of all of the kilonova models from the POSIS kilonova model grid from Bulla 2025, and requiring the criteria that we impose, so which is 3 detections in 2 filters, G and I bands. If we compare our limits, median limits from the campaign to the kilonova models, we can actually rule out 45% of the grid. And here you can see the blue models are the ones that are ruled out, and the gray are the kilonova models that are still consistent with our observations. So this is excellent. It provides a lot of potential for future follow-up and detection of kilonovae with Rubin. So yes, we conducted the first comprehensive search for an EM counterpart to a gravitational wave event with Rubin. The results were released via GCN in these 2 GCNs here, and the photometry we released on TNS. As this was a subsolar mass merger, we have the potential to probe new physics. Additional analyses are in progress, specifically to probe the super kilonova angle of this analysis, which I didn't really talk about in this presentation. And we plan for a paper to be released before IR1, and the observations will be released as a part of Rubin's data preview too. So finally, this is my last slide. I wanted to leave you with the key points from the talk, as well as some additional things to think about that we can discuss. As I mentioned, past experience shows us that systematic filtering really helps. And to maximize counterpart discovery in the future, we really need community filtering. I just want to quickly mention that we are actually developing some tiered ranking criteria at the TVS MMA telecons. So please join those when you can. And also join us for Rubin ToO 2026 at Berkeley for more discussion. Thank you.
Shreya, questions?
Thanks, Shreya, and a big shout out for the great work you and Sean, among others, have done. But this was impressive. I think the numbers show it. Something else that I know that you didn't quite mention is that actually for some time you have also thought yourself of applying machine learning models like other groups are now doing. And I just wanted your personal opinion. Like, where are we at right now? Like, not as individual tools, but more like as a community in employing this sort of rigid cuts that we have always loved so much versus using somewhat more innovative techniques for selection?
Yeah, that's a great question. I think there's a lot of potential there. So Natalia is actually going to address that hopefully in her talk, or if not, I think folks should definitely talk to her. I think there's definitely a lot of room for machine learning to be used in candidate selection. And there are definitely a lot of assumptions that we apply when we stick to our standard filtering criteria that may exclude certain candidates. Of course, we want to strike a balance. So maybe my suggestion would be to apply some very basic cuts that we know work, just to ensure that candidates that we select are real. And then from there, applying machine learning to actually select things that could be evolving the way that we expect a kilonova to evolve. I think that would be, excellent.
Thanks for the very interesting talk. I want to hear your thoughts a little bit of one of the crucial steps we have found for kilonova candidate detection. So we know the light curves are hard to get there, even though you're targeting with Rubin. It's the host galaxy redshifts. So a close by redshift, the photo-Cs usually have huge uncertainties. And one of the biggest things that we could do is do a spectroscopic redshift like 4HS is aiming to. But while we don't have 4HS, any thoughts about what as a community we should be doing to get better photo-Cs at low redshift?
Oh, I see. Yeah, so this is a really great point. I guess, to answer the first part, I guess, I think it's very hard to filter out things based on photo-Zs, especially when we're looking at these low redshifts. I think we need to take things with a pinch of salt, and especially draw quality cuts on the photo-Zs even as we are selecting them. I know that Rubin is also, there are folks at Rubin who are working hard on getting better photo-Zs, a better photo-Z catalog. And I think Rubin plus Roman will result in highly improved photometric redshifts that we can use, but that's a little bit further on the horizon. So there's some discussion about combining the two data sets to get really good photometric redshifts. Yeah.
Okay, we have to move on. I know there were more hands, so I hope you save your questions for the discussion at the end. And let's thank Shreya